to see if anybody wants to ask any questions about this example. I showed you my logic that I used to come up with this. I made an ice table, even though I don't think that you really need to in these questions, but I'm showing it to you here again, just out of principle. Whenever an acid reacts with water, I should get ionization of hydronium and that base. Since I had none of them to start with, I know that they should increase by X, and that the acid's concentration should decrease by X. But X is so incredibly small, and it's so incredibly small that when I round the concentration of my acid to 2 significant digits, I'm going to end up with the same number that I started with. So even though it's not perfectly exactly the same, we're assuming that it is. I'm representing hydronium and the base with an X because I know they're both going to have increased by X. Then I set up my Ka expression, which if I replace it with actual numbers, looks like this. Ka I found in the data booklet. So I found carbonic acid and I found its Ka. The 0.4 moles per liter was the concentration of the acid given in the question. And since hydronium and HCO3 negative are both X, I represented them with X squared. I figured out what X is by multiplying these two numbers here and then square rooting to find X. Then I did negative log of X because of course X is hydronium and that's what I need to find pH. And that's how I came up with 3.37. Now because that was similar to the first one, hopefully that makes sense, but does anyone have questions they want to ask about either of those first 2 examples about acids? Now if you were working on the questions on the acid side of the data review, this is essentially what you had to do for the second one. For the first one, it was a strong acid and you just directly found the pH, negative log of the concentration. Now, if we look at the third example, the last one, this was just a backwards question where we worked in the other direction. In this one, we know the pH is 3.07. So I could find the concentration of hydronium with this. I know that hydronium is 10 to the negative pH. So in this case, I would say it's 10 to the power of negative 3.07 or 0.000851 moles per liter. It's up to you whether you want to use scientific notation or not in your own work. If it was a question where you were reporting your answer, you would probably have to use scientific notation, only because you can't report something like that in a numeric response. There's too many zeros. Now, once I know this, what can I do with it? Well, think about what the reaction would look like for butanoic acid. So there's butanoic acid. How did I know what butanoic acid is? Well, I'm a chem teacher, so I know these kinds of things, but butanoic acid should have 4 carbons. I could draw it and figure it out, or I could remember that just like in the review, the data booklet has lots of answers, and I could have found the formula for butanoic acid there. If you're ever unsure what it should look like on the other side, here, hopefully because it said acid, you were like, oh, well, this is an acid, so it's going to make hydronium. But if you didn't know, use your data booklet. If it's in the acid column, it's going to make an acid. If it's in the base column, it's going to make a base. This is in the acid column, so hydronium. Now, what's this other substance? Well, it's whatever's left of my acid when I take away a hydrogen, and if I'm unsure, it should be in the column next to it in my data table. In this case, C3H7COO negative, which is butanoate as an ion. Now, that's my reaction, and I wrote it out so that I could visualize that this is the concentration of hydronium. It should also be the concentration of this ion because in the last 2 questions I said that they had the same concentration when I put my solution with water. So I'm going to continue with that assumption, saying that those 2 things, because they have the same coefficient, also have the same concentration. Now, if I want to calculate Ka, I should take the concentration of hydronium times the concentration of my base divided by the concentration of the acid. So I'm going to take 0.000851 squared because I'm saying it fits in both of those spots. I'm going to put 0.048 down here because that's the concentration for butanoic acid given in the question. Remember that Ka doesn't have units, so if you would like to omit the units as you're doing the calculation, just so you don't confuse yourself with moles and liters and liters and moles and squared and cubed and that kind of thing, you can. And it should give you 1.5 times 10 to the power of negative 5. Now, this was in your data booklet. Yesterday, Nicholas asked me if we just look it up if it's in the data booklet. Of course you can. I just wanted to show you that we would get the answer that was in the data booklet if we did this calculation. Now that's the acid side of the story. We also have to go over the base side of the story. So before we do, does anyone want to ask anything? Now, the base side of the story is basically the same as the acid side of the story. We're just going to replace everything where we had acid characteristics with base characteristics. Bases, unlike acids, have a bitter taste, although I do not ever want you to taste something in the lab to tell if it's a base. Even if it was food, you guys have seen how clean or not clean some of those containers are in the lab. Please don't ever consume food that came out of a lab container. It's gross. They're slippery, so they're the ones that feel like soap, that kind of slippery. Strong bases exhibit these properties more than weak bases, just like strong acids make more bubbles because they react more vigorously with metals than a weak acid does. A strong base is anything that contains hydroxide. So I've already shown you this in your data booklet, but hydroxide is the bottom line. It's gray. It's the only thing that's a strong base. Anything above that gray line would be a weak base. Now, there's a difference between a strong and a weak base. Strong bases already have hydroxide. Weak bases don't have hydroxide in their formula, but they will make some when they react with water. So, if I look at a strong base example, the ions dissociate completely. So when I put, say, sodium hydroxide in water, the sodium and the hydroxide ion will completely dissociate from each other. I know it's complete because I've got a quantitative reaction. I can see my arrow there. That means that these two will have the same concentration as my original sodium hydroxide. If I want to calculate the pOH, I take this concentration, which you'll notice is the same as the one that was given in the question. It gives 0.38. If I wanted to know the pH of this solution, I would do 14 minus the pOH, giving me 13.62. Now, strong acids and strong bases require like a one-step calculation. That's why it's not usually the only thing you have to do in a question. If the question is just asking you, what's the pH of this solution, it's probably a weak acid or a weak base, not a strong one. Now, if we consider weak bases, for the most part, they are all anions, so negative ions. If you look in your data booklet and the column that says bases, basically all of them are a negative ion. The only one I think really that's an exception to that you would use frequently is ammonia. Ammonia is NH3. But anytime a weak base is dissolved, notice it reacts with water. So it's not like a strong base where it just separated and water wasn't part of the reaction. The weak base actually has to react with water just like the weak acid does. We always get the acid that goes with it and hydroxide as our products. So if we were saying with words what happens, weak base reacts with water, makes an acid and hydroxide ion. Now, just like with Ka, the extent to which the reaction takes place is the base ionization constant. It's just K, but this time for a base. Notice when we set up the Kb expression, all I'm doing is taking the concentration of the products divided by the concentration of the reactants. That is the same thing we did for Ka. It's the same thing we did for Kw. It's the same thing we did for just regular old Kc. It's the same K expression. Just like with acids, we could say that that hydroxide ion concentration and the acid that are produced should have the same concentration. And I would generally represent them both with an X. For my original base, we're assuming that the initial concentration is more or less the same as the equilibrium concentration, just like for an acid. So it'll change, but it'll change by so little that it'll seem like it was the same amount. So we could calculate Kb the same way we calculated Ka, by knowing the concentration of the products and the reactants. We can also use Kb to find those other values. Now, does anyone want to ask any questions about this idea before we do the calculation example? So we know the pH of a sodium carbonate solution. So first thing I would do is look at the question and ask myself, what is that? Is that a base solution or an acid solution? And I would look and I would say, well, the pH was 11.66, so kind of sounds like a base. And I would look in my data table and I would confirm that. Now, is sodium carbonate in the acid and base data table? No, it's not, but carbonate is. Sodium is a spectator. It's Na+. Carbonate, CO3 2 negative, that's the thing that's actually going to be part of the reaction. Just like with voltaic and electrolytic cells, just because you have something doesn't mean it's part of the reaction. Some things don't react. Sodium ions are not a good acid or base. They're not going to do anything in this acid-base reaction. Now, carbonate is going to be my base. Negative ions act as bases. So if you're ever unsure and you can't seem to find it in the data table, pick the negative ion. It will be the base. So if I want to calculate Kb, I need to know what expression I'm using. So I would be starting from this point. My carbonate ion plus water. Now what do I get? Well, I get HCO3 and OH negative. So whenever I react my weak base with water, I get the acid that would go with my base. Essentially, I take a hydrogen and add it, and I get a hydroxide ion. Now, it told me in the question the pH was 11.66. So, pH could tell me POH, which could tell me the concentration of hydroxide. That's where I'm going to go with this. I know that if the pH is 11.66, that means that the pOH is 2.34. They have to add up to 14, so I did 14 minus pH just like I did in the previous question. Now to figure out the concentration of hydroxide, it's 10 to the negative pOH, and I end up with 0.00457 moles per liter. Please don't round any of these numbers at all. Store them in your calculator. If you're not confident you can store them in your calculator, write all of the decimal places, or at least 6 or 7 of them. Otherwise, you might round your answer just enough that it's different from the actual answer. Now, I said before that these two could both be x. So this 0.00457 could fill in both of those places in my KB calculation. Down here, my base, it said was 0.1 moles per liter. And even though that's not the equilibrium concentration, remember it's going to change so little that I can use that value. I should get as my value for KB 2.1 times 10 to the power of negative 4. No unit, because it's the equilibrium constant, not a concentration. Does anyone want to ask anything about that example? Now that's all great. That's assuming that I know the original concentration of my solution and the pH or the pOH. But sometimes I don't know both of those pieces of information. So sometimes I need to do what people ended up doing on the daily review, if they asked me about it, which was to compare Ka and Kb. So I have up there the reaction for methanoic acid and methanoate. See how they're the same substances here and here? So I'm showing you basically the reverse scenario. What would happen if methanoic acid was my acid? What would happen if methanoate was my base? When methanoic acid is the acid, it will ionize to form methanoate and vice versa. Now, if I were to write the whole Ka expression, I would say that Ka is hydronium times that methanoate ion concentration divided by the acid. And I would say that Kb is the acid times hydroxide divided by the base. So the same thing that we just wrote down in those examples. Now, what would I get if I multiplied Ka and Kb together? So if I took those two expressions and multiplied them together, if there was something that was on the top and on the bottom, it would get eliminated, right? So this and this, those would all be eliminated. Why? Well, look, there was a methanoic acid on the top and on the bottom. There was a methanoate ion on the top in one and on the bottom in the other. If I multiply them, they're going to cancel out. So what do I have left? Well, I have hydronium times hydroxide, which is what Kw is, very conveniently. So Ka times Kb equals Kw. Just like hydronium times hydroxide equals Kw. So if I wanted to find Kb, I don't have to necessarily know the concentration of anything. I just have to know the Ka from the data booklet. So if I want to know Kb, I would do Kw divided by Ka. If I needed to know Ka, I could calculate it as well, but I don't think that this version is one you would have to use a ton. This, I think that you would. I think it's very probable for us to ask you to calculate Kb, and you have to use the Kw value to get it. So if I want to know for hypochlorite what its Kb value is, I would go into my data booklet, to my acid-base table, and I would figure out where the hypochlorite ion is. Now, if you're like, man, I don't know what hypochlorite is, periodic table has polyatomic ions on it, but hypochlorite is on the base side near the bottom. If there's a Ka value there for the acid, so I'm going to use that K value that I found in the data booklet. And the K value is 4.0 times 10 to the power of -8. So I took Kw from my data booklet, Ka from the same line that hypochlorite was on in my data booklet, and I divided them. When I do that, I get 2.5 times 10 to the power of -7. So does anyone want to ask anything about that example? The other example then is asking us to go a little bit further, figuring out the pH of a solution of ammonia. So if I think about ammonia, here's its reaction. Now, how did I know what went where? Well, I know that ammonia is a base. If I didn't, I would look in my data booklet and I would find it in the base column. If I didn't know what else should be produced besides hydroxide, I would look in my data booklet and see what's next to it. Oh, look, it's the ammonium ion. Now, the question is asking me to find pH. So what will I do? Well, I will find the concentration of hydroxide. Then I will find the pOH, and then I will find the pH. That's my plan. So for me to find the concentration of hydroxide, I need that K expression. So I know that Kb should be equal to those two numbers, which I'm going to assume are the same, x squared, divided by 0.108 moles per liter. Now I'm missing 2 bits of information. The question didn't tell me what the concentration of hydroxide is, nor did it tell me Kb. But I can figure out Kb. I'll look in the data booklet. I'll see that Ka on the ammonia line is 5.6 times 10 to the power of -10. So I will do my Kw divided by Ka, just like I did before. Kw in your data booklet on page 3, 1.0 times 10 to the power of -14. Ka on the line that ammonia is on, so for the ammonium ion as an acid, was 5.6 times 10 to the power of -10. That is probably for whoever is leaving early, I'm guessing. Hi. Okay, got it. Bye. That's what it was. Now, with that calculation, I can figure out Kb. So Kb is 1.7857 times 10 to the power of -5. Now I have the same setup that I had for my weak acids. I multiply the concentration on the bottom times Kb. I do the square root to find x. X, which is the concentration of hydroxide, is equal to 0.00138873 moles per liter. Now you don't have to write all of those decimal places, but I'm just trying to remind you, you shouldn't round anything. Not unless you're at the last step of your calculation. If here you rounded your answer, you might get a slightly different pH or pOH in the end. To find the pOH, I do negative log of that concentration. That gives me 2.857. And to do pH, I do 14 minus pOH, and that gives me 11.143. Now, does anyone want to ask anything about this example?